All right. All right, so welcome back again. Yeah, so our next speaker will be Greta Panova from USC, and she'll be speaking on computational complexity and representation theoretic.
Thank you very much. Thank you for having me speak at this conference. It's a very special feeling for me because I grew up in Bulgaria and Sofia, and I was in this institute when I was a high school student. I was here for Olympiad preparation, and now I'm back. So now as a professor. So I must say, so I'm a combinatorialist. So I'm not going to talk about quantum group industrial algebras, unfortunately, but the closest topic that I can discuss is still within representation theory, and representation theoretic problems is motivated by that. And there will be something quantum here, but not that kind of quantum. So, okay. So let me start. Maybe this works. Okay. So of course, you know representation theory. Lambda usually denotes the highest weight. For us in combinatorics, we think of it as a partition, which is a stack of which we represent in here diagrams and all these things. Pretty sure everybody here has seen that, right? And so the number of partitions satisfy a nice generating function, no closed formula. And the next thing you can do with Young tableau is put integers inside the boxes so that each integer from 1 up to n appears exactly once, and they grow strictly along rows and columns. These are standard Young tableau, right? So, and standard Young tableau from a combinatorics point of view, if you're a combinatorialist, what kind of problems do we care about? We care about counting. So how many? So the first question, we see some kind of discrete structure and we want to count it. And for this standard Young tableau, there is this so-called celebrated formula, hook-length formula, which tells you as an explicit product formula for the number of standard Young tableau. Okay, so this is all very classical and basic. Now, where does this all come from? And in some sense, it does come from representation theory, which you guys probably like more. So the standard Young tableau, in some certain sense, indexes the basis of the irreducible spec modules that so they're play a role in, like, let's say, the Schur duality in the previous talk. And so the number of standard Young tableau, that formula I showed, is also equal to the dimension of the irreducible representation. So there is a combinatorial connection with what people here in representation theory. And then you can also talk about the counterparts, again, in this Schur duality. If you look at the reducible GLN module, so here I'm only doing things over C, and in this case polynomial representation, so there will be indexed again by, well, highest ways, but in this case going to be partitions of certain fixed of limited length by size of the group. And the basis is indexed by semi-standard Young tableau. So yeah, something you probably all know. And how do you study these representations from, like, a combinatorialist point of view, and so connecting to Renat's talk? So a very basic class of functions in the symmetric function world are the Schur functions, and they are actually the characters of the modules. And so if you, in principle, you can compute everything related here to the representation here using some Schur function manipulation and extracting coefficient. So in some sense, we have a tool. And for many things, it is sufficient. So here the sure functions are, of course, polynomials with non-negative coefficients, which are monomials correspond to the semi-standard interval. And again, you can compute the dimension of the irreducible representation using the variations of the sure function, which actually factors nicely thanks to the various formulas, determinant formulas for the sure function. Okay, so now to get to the topic of my talk, now that we've understood to some extent the irreducible representations in these very classical cases of the symmetric group and the general linear group, can take two tensor products of two irreducibles and decompose them into irreducibles. We can do this in this case, and the coefficients, the multiplicities with which each isotypic component will show up. In the case of the general linear group, these are the little Richardson coefficients. And they are indexed by three partitions, one of the mu and mu. And you can compute it by hand if you want. You can use the sure function. So you take product of two sure functions and you expand it into the sure function basis. Miraculously, thanks to the representation theory behind all of this, you get no negative coefficients. And of course, the next thing you're going to ask is, what are these coefficients equal to? So you have three parameters, one of them mu and mu, partitions. What are the coefficients equal to? So there is no longer going to be a product formula, but there is something what's called a positive combinatorial interpretation. And the little Richardson coefficient counts certain types of fillings of this skew-Young diagram. So I don't care about the details of this rule, but the spirit of it is important just to keep it in mind. So it is counting certain types of nice combinatorial objects. Okay. So here is one example.
So
Okay.
he did not prove it in 1934.
Yes, he did not. Yeah, so it was proven almost 40 years later. There were a lot of wrong proofs, and I must say that it's in combinatorics. It is a lot of combinatorics comes with algorithms or rules of various types. So you try few examples, you see, oh, this goes here, this goes here, this makes a nice structure. Okay, maybe this is how it works, and you write the proof, and very often the proof. I mean, the rule itself will also be wrong in the end. Maybe like some huge example is not true, but it is it is surprisingly difficult to prove this little Richardson rule. I've done this in class, and it takes me one lecture.
But he stated it correctly. They stated it correctly.
I think so, but I am not now in front of the camera. I don't know. Those will come up.
So McDonald has a joke about this.
Yeah.
What says, I don't know, it says something like, he was quoting somebody else and it says, the little Richardson rule helped put man on the moon. But it was not proved until after.
Well, I mean, on the other hand, sometimes you cannot prove something if it's wrong. So, but anyway. Okay, so maybe the little Richardson rule helped put a man on the moon. So can we put a man on Mars? I don't know if somebody finds a connection to the Mars mission. Okay, so now we can play the same game with the symmetric group representation to take irreducible two space modules, you tensor them together and decompose them into irreducibles. This time symmetric group representations, they're going to show up with certain multiplicities, which are non-negative integers by definition. These are the Kronecker coefficients, and again, they depend on three partitions, lambda, mu, and nu. For the ones who like sure functions, there is a way to extract this using sure functions again. This time, you take one of the sure functions, you substitute all pairwise products of x and y. So this is some form of plethysmic substitution. And you expand it into sure functions in x and y, and you group the terms and the coefficients that are in the two pairs, mu and nu, would be the Kronecker coefficient. And when you do this like that, it's not at all obvious that you're going to get non-negative integers. And but if you actually want to calculate this on a computer, for example, so I'm going to get to that, but a non-efficient way to do this is using three-dimensional contingency array. So yes, one can write the Kronecker coefficient as a sine sum over certain combinatorial quantities. These contingency arrays are just A by B by 3 arrays with non-negative integers, which have certain marginals given by L. But the question is, can you cancel those signs somehow and get something positive in the end? And similarly, you can take irreducible representations of general linear groups. So it's from one general linear group to another, and then to a third one, you can compose this map. This is called plethysm of these representations. And when you skip to the middle and decompose the whole map, it is going to decompose into some irreducibles with some non-negative integer coefficients as multiplicities. Those are called the plethysm coefficients, and you can do this with sure functions again. This time, basically, you expand the inner sure function as monomial with maybe repeating monomials, and you substitute them as variables in the next sure function and expand. So this is, you are allowed to do this. Of course, there is a more formal way of defining plethysm, but it works. Okay. And so, since we haven't put a man on Mars yet, we don't know what these integers count. So it's already Morgenthau defined these Kronecker coefficients in 1938, and he observed that in certain special cases, when the partitions have long first rows and the lower parts add up, these give you little Richardson coefficients. So little Richardson are strictly subcase of the Kronecker coefficient in some sense. And he actually had trouble computing them to begin with in any form, and he was wondering how to do that. And then later, this was picked up in the algebraic combinatorics community by Lascaux and Garcia and Ramel, and Richard Stanley coined it in his survey positivity problems in combinatorics in 2000. So this was problem number 10.
So G is the previous function. What is G?
G is the Kronecker coefficient. So G lambda mu nu is this Kronecker coefficient that is for the symmetric group and that we don't know.
So G is the Kronecker and C lambda mu nu
It
is
is the little
little
bit. And A is going to be the plethysm. So
yeah.
okay, so there are some formulas for various very special cases for G lambda mu nu. I'm going to show you one of them in a moment. But it's like measure zero whole cases that one would care about. So maybe the most general cases that we know is when one of the partitions is a single hook and the others are arbitrary, then this Kronecker coefficient is equal to the number of certain types of tableau with two different colors of entries with some kind of strings about them. This is due to John Lavoisier, and later was refined and simplified by Ricky Liu. And the same type of question holds for the plethysm coefficients. Is there a positive combinatorial formula? And of course, we care about this because why not? I mean, this is a natural combinatorial problem in algebraic combinatorics. We have some non-negative integers indexed by partitions. What do they count? But these problems actually are involved in other areas, including geometric complexity theory, which is a problem that's trying to prove lower bounds in computational complexity theory. And it's also related to quantum information theory, quantum mechanics even, and some other areas in physics who need to know something about these coefficients. And so the first question is, so this type of question, without defining combinatorial interpretation, it may never be answered. And so it is a good idea to actually try to define a combinatorial interpretation so that maybe one can disprove it. So maybe there isn't a combinatorial interpretation. Even though these are non-negative integers, maybe whatever the original definition is the best thing there is. And so before I talk about combinatorial interpretation, let me give you one example of a combinatorial interpretation that is not in the usual form of tableau that I showed earlier. So here we have partitions that fit in, integer partitions that fit inside a rectangle, graded by the number of boxes. This is combinatorial interpretation for the Q binomial coefficient. So this is the definition. And it turns out that Kronecker coefficient, when you have just a two-row partition rectangle, is equal to the consecutive difference between two of these things. So where can you do this with this short function that I mentioned? So what do you get out of this relation? The one thing you get is that this quantity has to be non-negative. And you may think this is trivial, so I challenge you to figure out why are these numbers weakly increasing until the middle, and of course afterwards symmetry. So this weakly decreasing, and using this type of interpretation, which this is not a combinatorial interpretation, yet it's difference of combinatorial quantities that happens to be non-negative. And in the end, we use the proof for the positivity of this Q binomial coefficients, consecutive differences of Katie O'Hara, to extract the combinatorial interpretation for this particular Kronecker coefficient when you have a two-row partition, rectangle. And yes, there are some tableau here in the picture, but the whole thing is you're counting certain types of trees that are labeled, the vertices are labeled by some partitions and two other integers, and the edges that come out of it are also labeled, and there are various relations. And in the end, you have some kind of a marking that you are living under some kind of some certain constraint. So that is the one, probably the shortest in some sense, although we have to work on this more to get it more compact from the complex theoretic perspective. But this is a combinatorial interpretation. And maybe even though the original formula may look simpler, but you don't get it is counting anything directly, and it is counting those types of structures. And the same type of thing we can generalize this for plethysm coefficients. When the inner partition is just a single row and the outer partition is just a two row. So these are SL2 basically. The SL2 cases of these plethysms can be completely classified as combinatorial instances. Okay, so any questions so far? Okay, so
Can you show the previous slide too?
this one?
Yeah. What is GOS trees? That was the one last.
Yeah, so I'm not gonna talk about this. It's complicated. Yeah, so it is even worse than the previous tree.
Oh,
Yeah. So the point is, it exists. It's out there. It's not your friend. Maybe you don't want. But be careful what you wish for, because this is what the formal. This is in at least is a combinatorial interpretation, whereas none of the other ones is. Okay.
You showed us how to write C in terms of G, but what about A? C was
Oh, so there is no direct relation as far as that. We have some conjectures that the Kronecker coefficients for lambda rectangle is gonna be greater than or equal to the plethysm coefficient for lambda and D, so symmetric powers. But we haven't proven it in full generality and in general. But there is a coincidence. So in that case here, the plethysm coefficient is equal to. So when mu is just a single row, it happens to be equal to the Kronecker, but this is very special. Okay, so okay, so what is the combinatorial interpretation? Especially if we want to show something does not have a combinatorial interpretation, one needs to formalize it somehow. And one way to do this is using computational complexity theory, because they already have notions very similar, and the computer science, theoretical computer science, they're concerned with counting formulas. And so when I say the little Richardson rule is an algorithm, RSK is an algorithm. So all of these things do already converge towards the area of theoretical computer science. So in computational complexity theory, there is one class of problems called decision problems. You have some input, if you want to know something about this input, you run your algorithm, it does certain number of steps, so you may be interested in limiting the memory or limiting the time, the number of elementary steps that it takes, and various other resources. And then it produces an answer. In the decision case, it's gonna be a yes or no answer. And you measure the input size in say bits. So this is your parameter. In this case, so input size is n bits. And then there is the class P. Well, the computational complexity class P is a class of problems where if you have an input of size n, so there exists for the whole problem, there exists a constant k, such that on an input of size n, you can get to the answer in at most n to the k many steps. And when I say steps, I mean like addition, multiplication, whatever. You can also use logical gates if you prefer, but polynomial it's going to be equivalent. And so it turned out that deciding if an integer is prime is actually can be done in polynomial time. That was the result. So linear programming, like if you want to decide if a system of linear equations has a real solution, for example, if a graph is connected, things like that, you can do it in polynomial time. And the counterpart of this is the class NP, which almost sounds like not P, but it means non-deterministic polynomial time. It is the class of problems where if the answer is yes, there exists a certificate or a witness called a witness, which you can check in polynomial time and know that, confirm that the answer was yes. And so the best way to do this is by example. So one of these NP complete problems is Hamiltonian cycle. So your input is a graph. You can think of it input as an adjacency matrix, zeros and ones, let's say simple graph. You want to know if it has a Hamiltonian cycle, meaning that you can go through every vertex exactly once by following the edges. So if you try to find the Hamiltonian cycle, you'll see that most likely you'll have to go through all possible permutations, which are vertices which are exponentially many. So there is no polynomial time algorithm that we know that will figure this out. But if there is a Hamiltonian cycle, I can just give you that cycle, and you can go through it and check in linear time that it is satisfies the condition. So that's the witness.
So NP is non-polynomial, right?
So NP means non-deterministic polynomial time. This is so the whole terminology starts with Turing machines. I don't want to go there. So there is deterministic, non-deterministic.
So you mean the K is not determined. What is not deterministic? So you say
So the Turing machine that verifies this is not there is a randomness involved, and so what is random in some sense here is that witness, for example. You cannot produce the witness, but once the witness is there, so maybe this is the non-deterministic part, you can check it quickly then. And of course, okay, so none of this would make sense if P is equal to NP, so let's assume for a moment they are not. Okay, and then there is the counting problems parts where again we have some input, you know, a non-negative integer function of that input. So here there are two classes, FP and sharp-P. So FP is where you can get the answer in polynomial time uniformly. All inputs, there is a particular K that you get it in to the K time. And you compute the determinant, spanning trees, recursions of various kinds, like number of standard young tableau. By the Cook-Lane formula, you can do in polynomial time and stuff. And then there is the class sharp-P, which is most interesting to us in this case, which is counting basically the class of functions which are counting those witnesses from the NP case. And if you want it completely explicit, so forget about the deterministic and non-deterministic part, sharp-P is the class of functions which can be expressed as a sum over exponentially many things. But each of these things is 0 or 1 and can be determined in polynomial time. But there is the same uniform algorithm which determines this in polynomial time, and this is, you can think of as this is the algorithm which checks if your witness is correct or not. So in this case, you just go over all possible cycles of vertices of Hamiltonian cycle, and for each one of them you count. You check if it's Hamiltonian. You can do this in many steps, so polynomial is many. And you count one if it is Hamiltonian cycle and the number of Hamiltonians.
Why use the abbreviation the FP and sharp-P? Why is
What
does FP means F?
functional
Function.
something like that. So, okay, so now. So now if you get fixated on the letters. So it's complexity zoo there. It's a letter soup, as they call it. So there are many classes, many complexity classes, depending on what kind of restrictions on the resources you impose. And we have very few separation results are known actually. So we have a hierarchy of computational complexity classes. There are some inclusions that are known, but many things are not separated, meaning there is no theorem that says that this class is strictly smaller. So here is our class sharp P. There is the class gap P positive, which is basically difference of two sharp P functions that happen to be non-negative. There is FQP. This is quantum. This is in the quantum computing world. This TISP means time and space, so we have restrictions on how much time and how much space we're allowed to use in our algorithms. And there is also the class sharp L, which is the class of counting problems where you can only use logarithmic amount of space to work and check your witness, and you can only read the witness once. So in sharp P, you have unrestricted access to the witness and polynomial amount of time to check what's going on. In the sharp L class, much more restricted. You can only use logarithmic amount of space, or you can do only small computations, and you can only read the witness once. And so there is the whole hierarchy. Well, not there are many more, but these are the ones we'll care about. And so here is the dictionary with our combinatorial interpretation stuff. If there is an efficient formula like a determinant, then the problem is in P or F. So the decision problem is in P, the counting problem is in FP. And these classes this is contained in sharp P almost by definition. The problem is in sharp P if and only if basically there is a positive combinatorial interpretation, because what is the positive combinatorial interpretation is counting the number of witnesses. Each of these witnesses is checked easily, so it's as nice as it gets in some sense. Then there is the class sharp L, which is subset of this, and then it is really small compact formula of certain type, so that's better than a determinant in a certain sense. And if the problem is not in sharp P, which is something that we proved for the characters of the symmetric group squared, we're not gonna get there maybe. But then there is no combinatorial interpretation that one can call for.
No, I mean, it's just not possible, or it's not available so far.
So we proved that the problem is not in sharp P unless the hierarchy collapses. Unless the hierarchy of the computational complexity classes collapses. So if P is equal to NP, all of this is meaningless, but otherwise.
So there's about like a permanent.
The permanent is sharp P complete. Yeah. So the permanent is somewhere here.
Yeah, okay. So,
And the Littlewood-Richardson rule is somewhere here, but we don't know if it is complete or not. We don't know exactly how hard the Littlewood-Richardson.
but these things are not like mutually disjoint, right? I mean, nice formula, efficient formula, does it make a precise mathematical sense?
Well, that's why we are trying to do that, right? So this doesn't make precise mathematical sense. This
Exactly.
makes a precise mathematical sense.
That's
So
right.
this is our program in some sense.
That's why.
Why the square or just?
Because the character can be negative, and all this computational, so we can take absolute value, but doesn't, just the computational complexity framework doesn't make sense of it. When the sharp P or all this is by definition of negative functions.
How do you prove that something is not in sharp?
Okay, well, hopefully we'll see if we get there. Okay. Otherwise, I'll tell them later. Okay, so, okay, how do you formulate something like that in computational complexity terms? Let's say little Richardson coefficients. Our prototype of combinatorial interpretation. So we have input the three partitions. So what's the input size depends how you encode these partitions. Actually, you can change the type of the problem itself. So you get positivity is the little Richardson coefficient of 0, and you can also compute the value of it. So this is LR. And so first of all, it turns out that deciding if a little Richardson coefficient is non-zero can be done in polynomial time, which is consequence of the Knudsen-Tau saturation theorem from 2001. Basically, it boils down to deciding if a polytope is non-empty, and this can be done polynomial time, which is different from deciding if a polytope has an integer point, which can be sharp P, which is NP complete.
But when you did the Hard inequalities there, right?
The what?
The Hard inequalities to decide this.
The which inequalities?
Hard, HORN. See the,
Oh,
Just-
yeah, the Horn inequality.
yeah, just the Knudsen-Tau will not do it. It will only say that you can go to like saturated, but
Yeah.
then you want to get the inequalities for the saturated. that's
But
problem.
but the Horn inequalities are basically describing the
The code,
polytope, the
Yeah,
code, but you don't need to do that.
What?
But you don't need to go through all of this in order to decide if you're starting with lambda mu and mu,
right?
and you want to decide
If,
if the little Richardson coefficient is non-negative.
right,
You can take there is another polytope, let's say or Bernstein-Zalevinsky triangle or some other polytope which is cut out by lambda mu nu r parameters and that have other points, and you can decide for that one if it has any, if it's non-empty or not. So you don't need, the Horn inequalities are bad in some sense.
So you-
They're kind of recursive.
Bernstein-Zalevinsky recipe is easier to deal with.
Well, if you just want to decide
Yeah.
if that particular polytope is non-empty, you can do it in polynomial. And there are still unknowns here in the little Richardson case because so this is a combinatorial interpretation and it is in sharp P. Basically, it's very easy to prove that one of these either whatever you can even use Bernstein-Zalevinsky triangles, for example, or any of these interpretations, checking that each one of them satisfies the inequalities is going to take polynomial time. So it's all easy to see that this is in sharp P, but we actually don't know if it's sharp P complete when lambda mu and nu are input in what's called unary, meaning that the input size is n the size of the partitions. The input size is on the order of the size of the partitions. We actually don't know how hard exactly the problem is. Might be easier then. And so here are the Kronecker coefficients. And for the Kronecker coefficients, we know they are NP hard to decide if they're positive, which already puts them strictly worse than the little Richardson coefficients, assuming of course P is not equal to NP. And Malmurik was the father of the geometric complexity theorem, so they show up in the computations, therefore obstructions, and he was hoping that there would be some nice formula for them, well, positive because we want to prove inequalities for them. So he conjectured that there would be in sharp P, and Igor Pak conjectures they are not, assuming some separation. One of this proof.
Compute cron is to actually compute the
The
cron
value,
coefficient,
Yes,
and cron positivity just whether,
it's 0 or non-zero, yeah.
yeah, 0 or non-zero.
Yeah, and you cannot even decide if, yeah, we cannot decide
But the first problem is easier than the second one, right? To decide whether it is 0 or not is easier than to
I
actually.
mean, from strictly speaking, we don't know that. So it may be that in order to decide whether the Kronecker is 0 or non-zero, we have to compute the actual value. And that's actually the only way I know how to do it right now. In general, so in order to decide, given me 3 partitions, I want to know the Kronecker, unless it's one of these special cases. I have to compute the whole thing, go through the exponentially large computations, get some answer in the end, and say, oh, yes. Yeah, so,
I see,
but that actually, if there was a combinatorial interpretation, that's actually one of the benefits, is that you could say that something is non-zero by just exhibiting one of these objects that it helps, like the little Richardson. Give you the tableau, you already know the little Richardson is non-zero. For the Kronecker, you have to just compute the whole thing. Yeah, at least that's the state of the art. Yeah.
I mean, what is your opinion about the last convention?
Well, I'll tell you in a moment. Okay, so the completely same business holds for plethysms. And I cannot tell you which one is harder, the Kronecker or plethysm, but basically it's the same state of the art. NP hard, sharp P hard, we don't know if it is in NP, we don't know if it is in sharp P, or maybe not. Yeah. Okay, so in the other direction, so this was the hardest cases, but in the lower area, like lower complexity classes, so you can talk about GL2 plethysms, for example, and you can ask the computational complexity problem, given mu, give me the plethysm coefficient. That gives me the multiplicity of a 2-row partition, so that's why it's GL2, and the plethysm of the vowel module will be mu over the symmetric power given by K. And so that one can be done in polynomial time. That's not difficult to check. But if you want to write it as a counting formula and see the counting complexity classes maybe in a better way, you can say that you can do this in logarithmic space. This is what this class means, logarithmic space. Sorry, polynomial time and log square space. So if we believe that we can remove this square here, in which case it's going to be in the class Sharpel, but we haven't been able to write this completely. And this is where we use the combinatorial interpretation that I showed. Well, I didn't quite show it earlier, but this is a more compact way of seeing those trees. I'm not going to explain what the trees are, but the point is that it takes small amount of space to check that the trees are what they are, and only polynomial amount.
So this AR is the plethysm.
Oh yeah, so this is this one. So
Yeah, okay. I see.
the same plethysm coefficient, and by definition almost, and this is also plethysm coefficient, and these other ones.
Oh, nice.
Okay, so on the question of whether I believe this is not in Sharpie or not, so there are some certain more recent developments. in the quantum computing. So I promised the word quantum, but it kind of shows something quantum computing here. So first of all, what are people trying to do in general is trying to prove, to find instances of what's called, it used to be called quantum supremacy or super polynomial speed, quantum speedups, basically problems for which the quantum computers are faster, like orders of magnitude faster than the classical algorithms that we know. And in the quantum computing, again, you can talk about complexity classes. So there is the QMA, which is the quantum analog of the class MP. And that means that, again, you're, in some sense, all the quantum computers are inherently probabilistic, so the analogy is not completely, it doesn't go completely true, but you can think of basically the class of decision problems where there exists a witness for which there is a quantum polynomial time quantum verifier. So there are polynomially many quantum gates. You pass the witness through, and then it starts to do a measurement in the end, and you say it's fine. And so from what we know, the classical algorithms are inside. NP is a subclass of this class QMA. And there is the sharp BQP, which is the quantum analog of sharp B. So it is you're counting some things that are verifiable by polynomial time quantum verifier, or actually, to be more precise, in the end, it is a dimension of the subspace of witnesses, because quantum inputs live in a Hilbert space. So there are certain differences that I don't want to get into too much detail, but there are something we know about these classes. So is also chart of GP, and it turns out that deciding the positivity of a Kronecker coefficient is in this class QMA, and computing the Kronecker coefficient is in the class sharp BQP. So, which already makes it not, as far as we know, not the same type of problem as the ones that we know are not in sharp P. So because Kronecker is not in sharp P, that would mean separation between sharp P and sharp BQP, which is on its own a very, very, very big result. I mean, it may be actually true, but the evidence points that maybe the Kronecker coefficients in the end would be in sharp P. So there is, so the way one does these algorithms is or constructs the quantum circuit, because that's what algorithms would look like here, is using certain types of Hilbert transforms, and there is a quantum Schur transform actually that can be implemented in polynomially many quantum gates, and it can actually use. So one day, okay, not much time, but so one day I was reading the news, and I see this some century-old math puzzle solved by quantum algorithm, and I'm like, oh, what is this problem? And it turns out this problem is Kronecker coefficient. Okay, and so they found some polynomial, that some quantum algorithm that computes Kronecker coefficient that runs in polynomial time for certain classes of inputs that are given by the dimension. So this is because we're working in those spaces with the projectors that actually make sense to Yeah, this is a parameter, the dimensions of these spaces here. And they asked whether there is a classical algorithm, so they assume that there isn't gonna be a classical algorithm that runs in polynomial time in those cases. But unfortunately, that's not quite true. So it turns out that many of those cases for which their algorithm runs in polynomial time can also be done in polynomial time in a classical algorithm, and but the way you do it is completely different from how the quantum algorithm works, and it's inherently going to be some kind of sine sum. The point is that it's only a few terms that are going to show up once you analyze the data, and in particular, this Kronecker coefficients for those cases, meaning that you have one partition that has a long row, first row, and the rest is fixed number of boxes. If the rest is a fixed number of boxes and your other partitions are growing, you can compute the Kronecker coefficient in polynomial time, which makes it in this class NP, which is also non-negative, is in the class sharp P, which in some sense means that there is a combinatorial interpretation. What is it? You compute the number, and then that is your going to be your combinatorial interpretation. So
Can you remind what was F nu? You defined earlier, but I forgot.
this is the dimension of the Speck module.
I see.
So if the dimension of one of the Speck module is polynomial, you can compute the Kronecker coefficient also. And the same business with the plethysm coefficient. So one thing we show that all of these plethysm coefficients are going to be in the class sharp QP using this quantum short transform. And again, there were just conjectures that maybe there is some regime in which there is no the quantum algorithm takes polynomial time and the classical doesn't. But again, so for most of these cases, we can do this in classical polynomial time. And in particular, again, for those cases, one has combinatorial interpretation if we follow the recipe that corresponds with this Sharp-Lee formalism. Okay. And so since I'm out of time, I'm not going to tell you how to prove that something is not in Sharp-Lee. So
Questions?
Can I ask one? Sorry. So suppose I take the saturated problem that, let's say for the Kronecker coefficient. So rather than asking if S mu is sitting inside S lambda tensor S mu, you just saturate S n lambda, sorry, S n mu sitting inside S n lambda tensor S n.
you mean you multiply everything?
Exactly.
Okay.
Yeah. Every piece of the partition I multiply by n.
Yeah.
And then the experience is that the problem, at least for the Lie theory, becomes easier because then it's a cone and you have very explicit inequalities and that decides it.
Yes.
So I'm just asking for the Kronecker coefficient. Is there a similar?
Yeah, so that is actually due to Michael Walter and collaborators, that is the saturated Kronecker coefficients eventually is non-zero, is zero or non-zero. This problem is in the class NP and in the class ONP, meaning that you have a witness for positivity and witness for zeroness.
Yeah.
And this is the intersection of these two classes, NP and ONP, which makes it basically strictly easier than the usual Kronecker IC.
But the inequalities are not, all the inequalities are not known, right? Is that correct?
Yeah, I mean, I haven't seen them explicitly.
Yeah, I mean, I tried that
I
once. Yeah.
I know their existence, and they are maybe polynomially made such uniform.
But the full set of inequality is not known, I suppose.
Just for normal Kronecker.
Yeah, no, for the saturated.
For the saturated, I'm not sure exactly what it's called. Yeah, I'm not sure.
Any questions? Go ahead.
Does it make sense to study for realistic versions in the classical setting?
Yes,
So the quantum obviously has inherently days.
yeah, so you can talk about, so there is the class BPP, there is RP, so there are various probabilistic counting classes in the classical setting, so you can ask the same types of questions. So is there EPP, so is there randomized algorithm that can give you an answer and things like that. So
But it just increases the zoo, doesn't it?
that it also increases the zoo, yeah.
Yeah.
But in those cases, somehow it doesn't help. At least. So for certain types of problems, it is easier to see why probabilistically it would make sense, but here, I don't see it. It doesn't seem to be any better.
Other questions?
I wanted to ask, at the end, you mentioned many results. How do they compare now with the Box conjecture on the Kronecker coefficient? So
That it's in sharp or not?
yeah, you disprove the conjecture or there
No,
was
so
some
the conjectures are still
open?
open,
Yeah, okay.
but because now it is in sharp BQP, it is less likely to be not in Sharpie. Let's put it this way. Or at least some, well, I didn't talk about this, but some of the methods that we have for proving something is not in Sharpie are probably not going to apply.
Okay. Any more questions? Go ahead.
So if you want to do something that does not have a efficient quantum algorithm, the assumption is still P equal to P not equal to NP, or is there some quantum complexity assumption?
Yeah, I mean, there are the quantum in the quantum computing, there is the. Yeah, so the assumption would be that BQP is not equal to QMA and things like. There is quantum polynomial.
Classically, the benchmark is P is not equal to NP.
Yeah.
But what is the quantum benchmark? Is there one?
I mean, so there is a notion of these types of completeness, and that some problem is not going to the global in quantum polynomial time. It's not as well. There is not such a big framework, but there is still such these notions you can make, and you can always make some assumptions. So all these classes that we mentioned, so every time there is a new class, most of the conjecture that goes with it is that column is different from the other classes. Yeah.
Okay. Other questions? Okay, now let's thank Greta again.